In this video, I'm going to explain what standard electrode potentials are and how we measure them using a standard reduction table. But first, I want to give you a little context and a little bit of electricity vocabulary so you know what those units really represent when we look at the standard reduction table. So first of all, a particle of electricity is called an electron, and the charge of that electron is 1.602 times 10 to the negative 19th coulombs. The movement of electricity, usually through a wire, is called electric current, and that's measured in amperes, shortened by the abbreviation A, and that's equal to a coulomb per second. Now, the force moving the electricity, this is what we are interested in. This is called electric potential. That's the force behind, you could say, behind the electricity or behind the electrons, getting them to move. And a volt is equal to a joule per coulomb. So what causes the electrons to move? Well, electric current is driven by differences in potential energy called potential difference. In a voltaic cell, the potential difference between two electrodes is called the cell potential. It's also called the EMF, or the electromotive force. It's that force that drives the electrons from one electrode to the other electrode. Remember, this is measured in volts, which is equal to a joule per coulomb. Now, if we have a positive potential difference, that would indicate we have a spontaneous process. So just to review, a spontaneous process is one that occurs by itself. And this is what we see in a voltaic cell. We see electrons moving by themselves because reactions occur by themselves. A negative potential difference indicates a non-spontaneous process. So this thing is not going to occur on its own. We're not going to see these in normal voltaic cells. So a little bit about a standard reduction table. Because every voltaic cell involves two half cells, it's not possible to measure the standard reduction potential of a half cell directly. So we use a reference cell. A reference half reaction is the reduction of H plus to H2 under standard conditions, and that's assigned a standard reduction potential of exactly 0 volts. So every half reaction on the table is based off of the reduction of hydrogen. So let's take a look at this reaction. Now, this is a net ionic equation for a reaction that occurs in a voltaic cell. And we have zinc turning into zinc 2 plus and 2 electrons. That's zinc losing 2 electrons, which is oxidation. So we have zinc losing 2 electrons to become zinc positively 2 charged and the 2 extra electrons. This is what would occur at the anode of that voltaic cell. At the cathode, we'd have the copper, and the copper 2 plus ions will gain 2 electrons and turn into copper metal. This is reduction, and it occurs at the cathode of a voltaic cell. So this entire reaction occurs at a voltaic cell. One side, one half reaction occurs at the anode, and one half reaction occurs at the cathode. Now, on a standard reduction table, we only see the reduction reactions. So this is really what we're trying to find. This is what we're looking for. And we can see this as it's written on that table. And if we look it up, we'll find it. And the voltage assigned to it is 0.34 volts. Now, that's compared to hydrogen. Remember, hydrogen is the standard, it's set to 0. So compared to hydrogen, this reaction will have a charge of 0.34 volts. Now, if we look at the zinc side, we won't see an oxidation reaction on the standard reduction table, but we will see the reverse. So if we reverse the sign of what we see, then we can assign it a value of 0.76. So to summarize that, the oxidation side isn't shown on the reduction table, but the reverse of it is, the reduction of it is. So normally for this reaction, the reduction of it, we'd see negative 0.76. But because this is oxidation, we have to just flip the sign, reverse the sign, and that makes it a positive 0.76. To get the cell potential for this entire cell, not the half cells, but the entire cell, we add the oxidation side and the reduction side together. And I get 1.10 volts for this reaction, for this entire voltaic cell. Now, a couple things to mention. This is a positive potential difference, which means that this is a spontaneous reaction. This is one that will occur by itself. Another thing to mention is that this is all measured at standard state, and that's 1 atmosphere of pressure and 1 molar solution and standard temperature as well, which is 298 kelvins. Let's take a look at the reverse of this equation, and I'll show you why the reverse of this would not be spontaneous. So if we have our oxidation reaction, and I'm showing the oxidation reactions in green here. So if we have our oxidation reactions, so copper losing 2 electrons to create copper 2 plus ion. This is our oxidation reaction, and this would occur at the anode. So we have losing electrons as oxidation. The zinc side is the gaining electrons here. So zinc is gaining electrons is reduction. The zinc 2 plus is really what's gaining the electrons to turn it into zinc metal. So we have reduction happening on the zinc side at the cathode side, and we have oxidation happening on the copper side or the anode. So we're just really looking at what would happen if we reversed this cell, this voltaic cell. So let's look up on our reduction table the reduction of this zinc. Well, if you find it, we get 0.76, a negative 0.76. And we will find this reduction half reaction on a standard reduction table. What we won't find is the oxidation reaction, but we will find the reverse of it. So all we have to do is reverse the sign. So negative 0.34 for this oxidation reaction. Now what you're going to see when we add these two numbers together is we get a negative voltage, a negative potential difference. Because it's negative, this is not a spontaneous reaction. This would not occur on its own in a battery. It's bad. The spontaneous reaction would occur in a voltaic cell. So let's practice using a standard reduction table to calculate the EMF or the cell potential difference for different reactions. And we'll start out with this reaction. Now what we kind of have to do here is we kind of have to figure out what parts of this reaction are the reduction parts. So what I do usually is I look at a standard reduction table and I find out which pieces match both on the left side of the arrow and on the right side of the arrow. So I have that Cr2O7 2- plus the 14 hydrogen ions gives us 2 Cr3 plus ions and 7 H2O molecules. I'm going to include the electrons in there, but you don't really have to. It's not a big deal. The standard reduction table includes them, but like I said, don't worry about it. So according to our standard reduction table, this, when compared with hydrogen, has a voltage of 1.33. Now, because it's the reduction reaction, we just keep everything as it is. The oxidation reaction is going to be represented in green, and that gives us, that is 6 I negative, gives us 3 iodine molecules and 6 electrons. Now we aren't going to see this reaction on our reduction table, but we will see the reverse of it. And on our table, we see that the reverse of it is a positive 0.54. But because this is an oxidation reaction, we need to reverse the sign of it. So it's going to be negative 0.54. So just for reference purposes, what you see on your standard reduction table is really I2 plus 2 electrons gives us 2 I negatives, and that's going to be at a positive 0.54. But we don't need that reaction. We want actually the reverse of it. We want the oxidation reaction. That's why we have to use the negative of that, or the opposite, the inverse of that. Now we're going to add these two numbers together and we get 0.79 volts. So that is the EMF for this voltaic cell, is 0.79 volts. One thing you're going to notice about these reduction and oxidation reactions is the reduction reactions will occur higher on the standard reduction table than the oxidation reactions. The oxidation reactions are going to occur lower, physically lower on that table. So if you're having trouble finding them, that table is actually listed in order of the reduction reactions are going to be more towards the top, and the oxidation ones are always going to occur underneath the reduction ones. That's the list, that's the order. So here we have another practice problem. What is the standard EMF for a voltaic cell based on this reaction? So our reduction reaction is written as is. We have 3 iodine molecules plus some electrons. 6 electrons gives us 6 iodide ions. And written as is, we can find that directly on the reduction table, and it's going to be a 0.54 volts. And now the oxidation reaction is the aluminum side of this. So we have 2 aluminum atoms, and that's going to give us 2 aluminum ions, and that's going to be losing electrons. Those aluminum atoms are going to be losing electrons. That's what oxidation is. So we represent the electrons on the right. Now, we're not going to find this exact reaction on the reduction table because this is an oxidation reaction, but we will find the reverse of it. And so what we need to do is reverse the sign, and that gives us a positive 1.66 for that oxidation reaction. We add those two numbers together and we get 2.20 volts for the EMF for this voltaic cell. A couple other practice problems here. If we have a voltaic cell and it's created using the following half reactions, a cadmium and a tin reaction, what we want to do is determine the half reactions that occur at the cathode and at the anode, and then calculate the standard cell potential. So how do we figure out which reactions are going to occur at the cathode and which reaction will occur at the anode? Well, in order to determine that, we need to figure out the voltage for each half cell. We have a negative 0.40 for the cadmium and a negative 0.14 volts for the tin. So what we're going to look at is which one is the most negative. That's going to be your anode. The anode is the negative, and that's going to be the one that is the most negative. That's going to be the half cell that is the most negative. That's going to be your oxidation. The cathode is going to be the one that's the most positive. That's going to be your reduction. So if you're wondering which one is which, if you're assigning which one will be the anode and which one will be the cathode, this is how you assign it. Now remember, one of these half reactions has to be flipped, and that would be the one that is on the oxidation side. So we flip the oxidation one. That reaction is actually not going to occur the way it's written because it's written as a reduction, and we want it to be an oxidation. So we're going to flip the sign on that as well. So we flip the sign to a positive 0.40 volts for the oxidation. We keep the reduction as it's written because the voltage is assigned for it as it's written, and it's written in reduction form. And that would equal a 0.26 volts. So 0.40 volts minus 0.14 volts, that's going to equal 0.26 volts. Now, if we're to write the overall net ionic equation for this entire reaction at this voltaic cell, it would be Sn2 plus Cd gives us Sn plus Cd2 plus. Remember, we had to reverse that oxidation reaction because it's written right now as a reduction, but we had to reverse it to make it an oxidation. One last practice problem. We have a voltaic cell, and it's created using the following half reactions. We have a copper and a silver. So the voltage on the copper, to go from copper 2 plus to copper, to reduce that is 0.34 volts, and to reduce the silver is 0.80 volts. So which one is the most negative? Well, that's going to be your anode. That's going to be the 0.34 volts. That's going to be where the oxidation occurs, and that's going to be, we're going to reverse that sign. So we're going to turn that from a positive 0.34 to a negative 0.34. Our reduction occurs at the cathode. That's going to be our silver measurement, and our silver ion turning into silver metal. So that's going to stay positive. So we have a positive 0.80 plus a negative 0.34 equals 0.46 volts.